Okay, so for this video, we will be discussing the integration of hyperbolic functions. So before we proceed with integration, so let's first review the definition of exponential functions. So, the definition of hyperbolic functions in terms of exponential functions. Okay, so we have here the definition for the hyperbolic function. So the first one is we have the hyperbolic sine of x. It is defined as e to the x minus e to the negative x over 2. Okay, so this one. And the definition for hyperbolic cosine is e to the x plus e to the negative x over 2. Okay, so please notice the difference. So the difference in sign, it's in hyperbolic sine it's minus e to the negative x, and in hyperbolic cosine it's plus, okay, e to the negative x. So for tangent, so we know that tangent is sine over cosine. So the same with hyperbolic tangent. So hyperbolic tangent is hyperbolic sine of x over hyperbolic cosine of x. So in terms of exponential function, so it's defined as e to the x minus e to the negative x over e to the x plus e to the negative x. Okay, so you can derive this by substituting the values for hyperbolic sine of x and hyperbolic cosine of x, no? So you put it there, and then the cosine for the denominator, hyperbolic cosine. Okay, so the same with hyperbolic cotangent. So hyperbolic cotangent is the reciprocal of hyperbolic tangent. So therefore hyperbolic cotangent is equal to hyperbolic cosine over hyperbolic of sine. And in terms of exponential function, so it's the reciprocal of hyperbolic tangent. So last one is for hyperbolic, last two is hyperbolic secant, which is the reciprocal of hyperbolic cosine. Okay, so its exponential definition will also be the reciprocal, no, of hyperbolic cosine. And the last one, hyperbolic cosecant, is reciprocal of hyperbolic of sine. Okay, so its definition is also the reciprocal of hyperbolic sine. Okay, so next is we also have hyperbolic identities for hyperbolic functions, which are similar to those of the trigonometric functions. So the first one, we have hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. So notice its difference with the trigonometric function. So in the trigonometric function, so the sign here is positive, no? So in the hyperbolic functions, it's minus sine hyperbolic sine squared x. Also, the other two, the next two identities are derived from the first one. So the second one, which is 1 minus hyperbolic tangent squared of x is equal to hyperbolic secant squared of x, is derived from the first one. Okay, so derived from this. So this is so the first identity, no, the hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1 will just be divided by hyperbolic cosine squared of x, no? So to derive the second identity. So the third identity is derived by dividing the first identity with hyperbolic sine squared x. Okay, so the other two, the last two, are similar with the double angle identities for the trigonometric functions. No, the only difference I think is this one, the positive sign So in the double angle identity for trigonometric functions, so that's cosine squared x minus sine squared x. In the hyperbolic functions, the hyperbolic cosine of 2x is equal to hyperbolic cosine squared of x plus hyperbolic sine squared of x. Okay, so the last one is for the integrals, no, formula for the integrals. So as you can see, we have there the first column are for the derivatives of the hyperbolic functions, and the second column is for the integrals, no? So if you notice, it is similar with the integrals of trigonometric functions. So the only difference are the signs, no? So you have to take note of the signs, no? So say for example the second row, okay? So in differential calculus, the differential of hyperbolic cosine of u is equal to positive hyperbolic sine of u. No, so if you recall, in the trigonometric identities, the derivative of cosine is negative sine. No, however, in hyperbolic functions, the derivative of hyperbolic cosine is positive hyperbolic sine. So it's similar with the integral. So the integral of hyperbolic sine of u du is equal to positive hyperbolic cosine of u. So I think the other signs that you should take note are that for hyperbolic secant, and so I think only those two. Okay, so only those two, no differ in sign with the trigonometric functions. So please memorize these formulas because we will be using that for our following examples. So in certain cases also, we might use u substitution for the integration. So we have to take, if we let u as e to the x, so then x is equal to ln of u, and dx is equal to du over u. So we might use that for our next examples. Okay, so now let's apply those formulas in some problems. So say for example, we have here number 1. So the integral of x squared hyperbolic secant of x cubed hyperbolic tangent of x cubed dx. Okay, so as we can see, obviously it's a direct use of the integration formulas for hyperbolic cosine. So hyperbolic functions. So specifically the integral of hyperbolic secant of u hyperbolic tangent of u du is equal to negative hyperbolic secant of u plus c. Okay, so let's inspect the example. So we have here, so this is similar with this, now with our u as x cube, right? Okay, so therefore it's complete differential, no? So we should find du to complete the differential. We have the differential of x cube is, that is our du. So differential of x cube is 3x squared dx. Okay, so let us rearrange this, no, so that it will become in this form. So we have integral of we have hyperbolic secant of x cube, no, times hyperbolic tangent of x cubed, then multiply with this one, x squared dx. Okay, so to complete the differential, so the complete differential is 3x squared dx, so this is only x squared dx, so we need to place a coefficient there, 3. So to balance that, so outside the integral sign, write the reciprocal of 3, now which is 1/3. Okay, so with that, so this we can now apply the this formula, no? So it will become negative, so write first 1/3, so 1/3 multiplied by integral of this is negative hyperbolic secant of u, so our u is x cubed, and then of course plus c. Okay, so rewriting that, we will have negative 1/3 hyperbolic secant of x cubed plus c. Okay, so another example, so let's have example 2. We have integral of, let's say we have integral of hyperbolic sine of 2x over 1 plus hyperbolic cosine of 2x dx. Okay, so in that problem, so we can solve that using integrals that lead to logarithmic functions, no? So particularly the natural logarithm. Okay, so here, so let's review our formula for ln. So integral of du over u is equal to ln of u plus c, no? So in this problem, our u is equal to 1 plus hyperbolic cosine of 2x. Okay, so therefore the du is its differential, so differential of 1 is 0, differential of hyperbolic cosine 2x is hyperbolic sine of 2x, and then by the chain rule, so multiply with the differential of this, so 2 dx. Okay, so therefore our du is 2 hyperbolic sine of 2x dx. Okay, so our complete differential, the numerator should be with a coefficient of 2. Okay, so right here 2, then outside the integral sign, write 1/2 to balance the numerical coefficient that we added. So this will become 1/2 ln of u is 1 plus hyperbolic cosine of 2x, okay, plus c. So other form, you can write this, you can write the exponent, the coefficient as the exponent. So it will become ln of 1 plus hyperbolic cosine of 2x plus c. So ln of 1/2 hyperbolic cosine of 2x raised to 1/2 plus c. Okay, or you can write it as a radical, so ln of square root of 1 plus hyperbolic cosine of 2x. Okay, so any of these three can be your answer. Okay, so for the third example, so we have the integral of hyperbolic cosine squared of x dx. Okay, so in this problem, we can see that we don't have the direct formula for the integration of hyperbolic cosine squared of x. So we might want to use the identities for hyperbolic functions so that we can convert this into a form wherein it can be integrated. Okay, so since we have here a cosine square, hyperbolic cosine squared, so let's recall the identities that have hyperbolic cosine squared in them. So the first one is hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. Okay, so another one is let's see, so we have hyperbolic cosine of 2x is equal to hyperbolic cosine squared of x plus hyperbolic sine squared of x. Okay, so since we'll only be needing the hyperbolic cosine squared of x, so let's replace the hyperbolic sine squared of x using the first identity. So from the first identity, we can see that if we transpose the hyperbolic sine squared of x and then transpose 1, so we will have hyperbolic cosine squared of x minus 1 is equal to hyperbolic sine squared of x. Okay, so let's use that to replace this. So we will have hyperbolic cosine of 2x is equal to hyperbolic cosine squared of x plus, so replacing hyperbolic sine squared of x with this, so we will have hyperbolic cosine squared of x minus 1. Okay, so simplifying that, we will have hyperbolic cosine of 2x is equal to 2 hyperbolic cosine squared of x minus 1. Okay, so since we will be needing the hyperbolic cosine squared of x, so transposing 1 on the other side and then dividing both sides with 2, so we will have hyperbolic cosine of 2x plus 1 is equal to 2 hyperbolic cosine squared of x. So dividing both sides with 2, we will have 1 half hyperbolic cosine of 2x plus 1 is equal to hyperbolic cosine squared of x. Okay, so using this, so replace our integrand with this, so our integral will become, so the integral of hyperbolic cosine squared of x dx is equal to integral of, so this, so 1 half times hyperbolic cosine of 2x plus 1 dx. Okay, so distributing the 1 half, the integral sign, and then the dx, and since 1 half is a numerical coefficient, so we can write it outside the integral sign, so this will become 1 half integral of hyperbolic cosine of 2x dx plus 1 half integral of dx. Okay, so take note of the integral of hyperbolic cosine. So the integral of hyperbolic cosine of u du is equal to hyperbolic sine of u plus c. Okay, so our u here is 2x. So therefore, our du should be equal to 2 dx. Okay? So as you can see, there is a missing part in the differential. So the differential is still incomplete. So to complete our differential, so we will have 1/2 integral of hyperbolic cosine of 2x times dx. So we have a missing 2, no, numerical coefficient. So write there 2, and then here outside the integral sign, so write the reciprocal of that numerical coefficient. So the reciprocal of 2 is 1/2. So we write that there, and then plus 1/2 integral of dx. Okay, so now we can integrate this. So 1/2 times 1/2, that is 1/4. Integral of cosine hyperbolic is positive hyperbolic sine of u. So our u is 2x. And then plus integral of dx is x. So 1/2 of x plus c.